are all very, very welcome. Thank you so much for joining us tonight for our presentation. Dr. Christina O is tonight's presenter, and she's going to be providing us with an overview of a solar storm at Mars. Dr. O is a assistant research physicist at UC Berkeley Space Science Laboratory. She received her PhD in Earth and Planetary Science and Space Physics from UC Berkeley before working as a postdoc at the Air Force Research Lab, then at Boston College. So her work on the MAVEN mission is devoted to understanding the effects of space weather events on the upper atmosphere and at the surface of Mars, and we're delighted to have her here with us. So, Dr. O, thank you so much for joining us.
All right, thank you for inviting me to participate in this webinar. So should I go ahead and share screen at this point?
Yes, that would be great. Go ahead.
Let me do that. Let's see, share screen. Let's see, so maybe I should maximize this. Can everyone see my whole screen? I'm not sure if anything got chopped off.
Yes.
Okay.
It looks pretty good. It looks good. Thank you.
Okay. All right. Well, today I'll talk about the big solar storm that happened in September 2017, over a year ago. So let me just dive right in, because I think I want to make sure I keep track of time here. So just a really, really brief intro about Mars. You know, we live on planet Earth, of course. You know, people always ask me, like, just some facts about Mars. So here's some facts, you know. So the diameter of Mars is 53% of Earth's, and its mass is 10% of Earth. And there's no volcanic activity at this point, unlike Earth, and it pretty much stopped like 3 billion years ago. The gravity is also lower on Mars as well. It's 38% of Earth's gravity. And so the escape velocity is really low. And because of that, the atmosphere of Mars can escape pretty easily. So why am I talking about this? Part of it is because the space weather will have an influence on all this, on the atmosphere of Mars. One of the factors that leads to atmospheric escape of Mars, which is a big topic that everyone likes to study, is in part because there's no global magnetic field at Mars, unlike planet Earth. So that's what I'm showing here in the graphics. This is sort of a cartoon illustration of what we call the dipole magnetic field at Earth, and hopefully you can see my mouse moving around the figure. This is what we have at Earth. At Mars, we don't have a global magnetic field. Instead, we have these little, what we call crystal magnetic fields, mostly in the southern hemisphere. Atmosphere at Mars is also very thin. Basically, if we were to live at Mars, is kind of like living in the stratosphere of Earth. So that's what the bottom graphics is showing on the slide. And so the lack of a global field and a thin atmosphere, those two combined means that there's not a lot of protection at Mars. So protection from what? Okay, so one is, you know, protection from space weather events. So this is a cartoon, it's very complicated, but what I'm trying to just illustrate here is what happens when the sun is very active. And so if you look in the upper left, you have a figure of the sun and something labeled called CME, it's coronal mass ejection. So when you have eruptions at the sun, this sort of this bubble of mass, charged particles, magnetic fields just kind of erupts off the sun and just goes radially outward into the solar system. With that, you have something called SEPs, that's solar energetic particles. And they stream along the magnetic field lines that are emanating throughout the solar system. You also have from the sun EUV, extreme ultraviolet. So that, you know, imparts photons everywhere, so also on the atmosphere of Mars. So bottom line is there's a lot of energetic input into Mars, and without a global magnetic field protecting it, with a thin atmosphere, a lot of these energetic inputs can have some interesting effects, different than those what we experience at Earth. And one big question I talked about earlier was, you know, what's the atmospheric loss at Mars right now? And this leads to, you know, where did the water at Mars go? I'm not going to talk about that topic. That in itself is a big topic that I'm not an expert on. But that's one of the motivation for studying space weather at Mars, studying the, you know, the effects of solar storms at Mars. The other motivation for studying space weather is, of course, there's all this interest to send humans to Mars, to colonize Mars, to live there. And so with a thin atmosphere and no global magnetic field to shield energetic particles, for example, there's harmful radiation at the surface. So unlike us living at Earth, we have this global magnetic field sort of shielding us from galactic cosmic ray particles, GCRs. At Mars, that's not the case. The GCRs, these highly energized particles, they will reach the surface. And if you live on Mars, what is the what are the impacts of the radiation over a long period of time? And this is also a question that people ask, in terms of when we travel to Mars, that that is also can be dangerous too. So there are people in the community trying to assess the radiation dosage and what are the implications for traveling to Mars and living on Mars for certain periods of time. Okay. So the topic of this talk is the solar storm, and particularly the one that occurred last year in September. So what I'm showing here on the left is a figure taken by the Solar Dynamics Observatory, SDO, that is near Earth. There's an imager on there, and that's what you're seeing here, an image. And it's a funny color of the sun because the image is taken with a particular filter to bring out certain features. But what I really want to show and draw your attention to is this bright feature on the right-hand side of the sun. So right-hand side in solar heliospherics lingo is what we call the west limb. I'll try to avoid using that. So if you look on the right-hand side of this figure, you see this sort of bright splotch. That's actually an eruption of what we call a solar flare. So solar flare, different from a CME, solar flare is a very localized eruption that doesn't propagate outward into the solar system. It's near an active region of the sun, and it's just it's an eruption that's fixed at the sun. So it's a solar flare. And what was really striking about this solar flare for those at Earth, but also for Mars, was that this solar flare was very long duration, lasted an hour. And it was very, very strong. So if you think of earthquakes and Richter scales, this is what we call the X-class flare. So there's like B class, C class, M class, and this X class. So it was very strong. What I'm showing here on the right is a movie of the, also from SDO, but at a different wavelength. And it's showing this, so while we have an X-class flare going on at this active region of the sun, there's also CME eruptions, and that's what I'm showing in this movie. And I'll show it again. So the CME was very fast, and it was very strong, and you can see, maybe you can't, but there was actually a shock wave that propagated across the surface of the sun. So in the solar community, this was a very exciting event in itself for solar physics. Okay. Now, I'm showing a cartoon here, so sort of to illustrate what I said earlier. So you have a solar flare. This is an event that is local at the sun. There's an eruption that goes on. That's a solar flare. And you also have this big bubble here, which is the CME. So I show you up here in the upper left, just an image of a solar loop. So this is not a CME, but it could be if it were to erupt off the sun. And for scale, you can see planet Earth right here. I don't know if you see this little dot, but that's planet Earth. So this gives you a sort of scale size of how big these loops from the sun are. Okay, so back to this cartoon, you have something called CME event, this coronal mass ejection that's going on, a solar flare. And what I want to sort of emphasize here is this concept of magnetic connection to these events. So the sun, there's magnetic field emanating from the sun, and it goes all over the solar system. And you can think of it as field lines. And so these field lines aren't going straight. If you were to take a snapshot of it, it's actually kind of like creates a spiral structure. So you can think of it as like a water hose in a garden. If you took a water hose that's flowing with water out, and you start spinning it, it creates sort of the spiral shape. So you can think of the interplanetary magnetic field from the sun having a similar shape, so it's a spiral configuration. We call it Parker spiral. Okay, so what you see here are these blue lines sort of giving you a cartoon configuration of the interplanetary magnetic field, curve, spiral. And you have planet Earth here sort of stuck to one of these lines. So that's what I mean by magnetic connection. And if you trace this field line from Earth back to the sun, that's what I mean when I'm saying magnetically connected back to the source. In this case, the flare or CME. So I hope that you can sort of have this cartoon picture in your mind as I'm talking about these events, because that'll be important. Okay, so basically for this in this cartoon, but also for the September event, Earth was actually magnetically connected to the source region back of the sun, where the flare activity occurred, where the CME eruption occurred. And so Earth actually saw some really intense energetic particles. So I talked about the figure on the left, now I'm talking about the figure on the right. So this is a movie stitched together using images from a coronagraph on board SOHO, which is an observatory upstream of Earth. So it's kind of near Earth. And you can see this bright sort of bubble coming off to the right-hand side. That's the CME. And you can see sort of this sort of snowstorm, like bombardment in the movie. That's actually the solar energetic particles hitting the camera. And this occurred tens of minutes after the CME erupted locally from the sun. And so because of this magnetic connections of Earth to the source region back of the sun, you can see the energetic particles right away. Now these energetic particles, they're charged, so they're bound to the magnetic field lines. So they kind of gyrate along the magnetic field lines, the electrons and the protons. So they can't just go off in any direction, they have to kind of follow the field lines. And so Earth is magnetically connected to the source region, to the CME, and the CME, moving out really fast, is accelerating energetic particles. And so you see these SEPs, these energetic particles, hitting the camera. Let's see, let me stop to answer questions if there are any. Okay, I'm seeing Christine shaking her head. Okay, I'll keep going. Okay, so this is a time series that I put together. So let me focus on the left side first. On the left column, label A, put POV, point of view from Earth. There's just a still image of the sun from SDO, and I kind of labeled here AR, the active region, and the CME loop. So you can sort of see the CME going off early on. So this is kind of like, I put the timestamp here on September 10th. And below it is a still frame of the LASCO movie that I just showed of the CME. So you can see some of the energetic particles already hitting the coronagraph at this point, but they're still streaming down the field lines, and at some point it's going to be like a snowstorm looking scene. On the right hand side of this figure set, I'm showing similar images from a different observer, so not Earth, but stereo. So if you look at the far right figure here, I kind of showed 3 observers. You have Earth. So this figure is basically you're looking down on the ecliptic plane. You're looking more or less over the North Pole of Earth. Okay, so you can think of that. And so here's Earth, here's Mars. So the sun's in the middle. I label AR for active region, sort of to give you an idea where is the solar activity coming off of. And here's something called a label STA, that's stereo A. So there's this other spacecraft that's along the orbit of Earth, but separated away from Earth. And it's just orbiting around. At some point, it'll kind of meet up with Earth again, but it'll kind of go along its merry way. Anyway, stereo A also has a coronagraph, and it has imagers of the sun. And I'm showing similar figures here of the CME at the bottom and also the active region at the top here. Okay, on the far right hand side, I'm showing some time series, and the point is I wanted to sort of emphasize that Earth saw the energetic particles really early on, pretty much within tens of minutes after the coronal mass ejection occurred. And so you see this sort of like very prompt arrival of energetic particles, very straight up, and then you see the particles, the count of the particles kind of dropping down over time. Mars also saw the solar energetic particles, and so did stereo A. And I'll kind of get into the Mars observations throughout this presentation, but the point I wanted to have you take away was that there were 3 observers during this event that measured energetic particles, which is quite exciting in the solar and heliosphere community, because it's not often that we have assets throughout the inner solar system measuring things. So that's exciting for that community. Okay, any questions? Okay, if not, I'm gonna go on to the simulation. Okay, let's focus on the left-hand side of this simulation. Okay, you're looking down on the ecliptic plane again, and I have labeled here planet Earth. You have Mars on the left side here where my mouse is hovering. You have stereo A, and you can see these sort of moving dash white and black lines here. That's just to illustrate the magnetic connection of the observer back to the sun. Okay, what is the simulation showing? Okay, the colors are showing the solar winds. So the solar winds all over the solar system, and it's just charged particles emanating from the sun, and embedded in the solar wind is the interplanetary magnetic field. And that's what the colors show. And this simulation was made for an entire month of September. So this active region that I talked about earlier at the sun, it actually stayed on, it was at the sun for quite a long time. So active regions of the sun can appear in the sun, and it can stay for one solar rotation, it can stay for half a solar rotation, it can stay for many solar rotations. This is what happened in this case. This active region actually was stuck around, no pun intended, on the sun for several months. Like the solar folks, we started seeing the active region back in June of 2017, and we kept monitoring it. Every time the sun rotated back and we saw the active region, we made note of it. One rotation later, we saw the active region again, and in September, it became super active. And so as a result of its activity, there's all these CMEs that erupted from the sun, and we got all this sort of space weather activity in the solar system. So the one that impacted Mars erupted from September 10th. Here you go, right here. So it was actually a series of 3 CMEs. So here's some still frames of this movie that I just showed. And I'm focusing on the time frame between September 10th, so that's panel A, through September 13th, that's panel F. So I'm showing sort of 12-hour snapshots of the movie shown previously. And I labeled here in each one the CME. So it says CME 1 plus 2, because there's actually 2 sort of wimpy CMEs that erupted late on September 9th and early September 10th. And then the big one happens later on September 10th. So because the first 2 CMEs were kind of slow and wimpy, by the time the September 10th CME that occurred later in the day, by the time that erupted, that was really fast. It actually caught up with the first 2 CMEs and sort of merged behind it to create sort of a merged CME structure. And the prediction from the simulations predicted for the impact at Mars to be on September 13th. And so I like to use these simulations in my research, partly because it gives sort of a global context of what's going on in the inner solar system. Also gives some context for the measurements that are being made at Mars, but also at Earth. And I like to sort of have a big picture understanding of what's going on. So I use these simulations a lot. And these simulations, if people care to know, are from the model called Wang-Shili RG. They're the last names of 3 people who over time developed this simulation tool, and it's coupled with the solar wind model called NLIL. So WSA NLIL for people who are interested in learning more about this modeling system that I'm showing here. Okay, so what I want to highlight here is panel F. So this is the prediction for Mars, and the prediction said that we're not going to get impacted until around September 13 at Mars. And then you go back to panel A, I also want to emphasize 2 things. One is, if you look at Earth, Earth has this black and white dash line threaded through it, and you can see that if you trace it back to the sun or near the sun, you can see that Earth was magnetically connected to the activity region in September last year. Whereas Earth, if you look over here for Mars, if you look at Mars, if you trace the field line back to the sun, it was not magnetically connected to the CME nor the flare It was never connected to the flare site, but it was not magnetically connected to the CME until much later on. So I want you to keep that in mind. Okay. Now, this event was neat also because this was the first time that there were a number of assets around Mars that was able to make measurements. So we have MAVEN, which is the Mars Atmosphere and Volatile Evolution spacecraft orbiting around Mars. We also had Mars Express, called MEX, also orbiting around Mars. And there was also at the surface, the Mars Science Laboratory making measurements. So what I'm going to show in the next set of slides are the measurements from these 3 missions. Now, there are other spacecraft orbiting Mars as well. Now, you have Mars Odyssey. There's also Trace Gas Orbiter, but I'm not going to show the measurements from those missions. Okay. And just one more thing, there was, prior to this event, the biggest event that the Mars community knew about, that I always get excited about, is what we call this Halloween event that occurred in 2003. But at the time, only the Mars Global Surveyor was around, and the Mars Odyssey was around, but it didn't have the suite of instruments that were available from MAVEN, MX, and also MSL. So that's another reason why this was a very exciting event for the Mars community to study. Okay, so this is a complicated plot, and don't get too bothered about the details. I'll kind of go over each panel, but in a general sense. So these are the observations from MAVEN, MEX, and MSL sort of stacked together. And part of my research was to figure out from all the little pieces of measurements that we get, sort of like a puzzle for me, like, what did we see? When did things happen? I see what was happening in the sun, and I can use the WSA-Enlil model to sort of give me an approximation for when things may occur at Mars. But what did the instruments actually measure? Keeping in mind that the instruments are, just a single point, in space, whether it's in the orbit around Mars or at the surface. So this is just a small piece of the puzzle, but any measurement that we can get can help us to better understand some of the space weather effects from a solar storm. Okay, so panel A at the top shows a time series. So x-axis is time, and what I'm showing on panel A is just a measurement of what we call solar irradiance from the EUV monitor on MAVEN. This is basically measuring flare activity. And so Mars actually observed the flare measurements at Mars from EUVM. And that's very exciting because this is the first simultaneous measurement of a flare at Mars and at Earth. But what I'm showing here is just Mars. And I labeled the magenta line here F for flare. If you trace it down, I'm highlighting 2 panels here. So first on panel K. And this is just a temperature measurement at 170 kilometers. And what I'm trying to point out is that, when this flare occurred, the photons, hit the Martian atmosphere and the temperature increased. And at the bottom, the panel below that, panel L, you can see measurements from the neutral gas and ion, NGIMS instrument, making measurements at a higher altitude, 195 kilometers, and they also see a temperature increase. And so what this panel L is showing us are the argon measurements. And why are we looking at argon? Well, argon is an inert gas, so it's a nice indicator when you see changes in argon temperatures that there are changes happening in the upper atmosphere. And that's what this is just a cartoon showing the layers of the different atmosphere of Mars and what the components make up the different layers. So in this case, you can see argon in the upper atmosphere and what they call the well-mixed atmosphere. And when you see argon temperatures increase, you can pretty much know that the atmosphere, the neutral atmosphere, also increased in the temperature. Okay, the next panels that I'm showing are the energetic particles, the SEPs. So I'm showing in panels B and C the measurements that are made by two instruments, one on board MAVEN by the SWIA instrument, and one by MEX, the Aspera 3 EMA instrument. And what this is basically showing is that now these instruments, they don't directly measure the energies of the particles, but when energetic particles go through the housing of the instrument and hit the detector, they see it as an increase in the background counts. And that's what you're seeing in this plot here. They saw an increase in the background counts. And for SWIA, this is caused by protons with a few tens of mega electron volts, so MeV, and also could be from electrons as well, a few MeV electrons. The MEX instrument saw an increase in the background counts from 20 MeV protons and from greater than 1 MeV electrons. The panel right below that is from another MAVEN instrument called the SEP instrument. It's unfortunate, it's a SEP instrument measuring SEPs. And I'm showing just two time series here to highlight that it measured increase in the count rate from two populations of protons, basically the 15 to 100 MeV protons and the those that are larger, the 80 to 220 MeV protons. Okay, at the bottom, oops, let's see. Okay, so, oh, right. So here I want to highlight the observations from MEX. So MEX has been around Mars since 2004. So it's been making measurements for quite a long time. And it's been continuously measuring background counts when there's energetic events going on. But this was the first time that the team members were able to sort of cross-calibrate measurements from MAVEN with their own instruments. So this was really cool. And the point of this figure is to just highlight the fact that this was the fourth largest SEP event that was measured by MEX since they've been around. So, so Robin Ramsat did some work on this, and he pointed out three bigger events that happened earlier in 2005, 2011, and 2012. So this is the fourth biggest event measured by MEX, but this is the first event that sort of simultaneously measured by another instrument on another mission. So this is really neat result. Okay, so NHR particles, they're hitting the atmosphere of Mars, but only the most energetic ones can actually reach the surface of Mars. And if we're talking about protons, then the proton would need at least 150 MeV energies to reach the surface. So this is what this cartoon is sort of showing here on the left. And you see the two curved lines here sort of to mimic the Parker spiral, the interplanetary magnetic field line, the curvature of it. And it's color coded by the time series here because I'm showing two population and measurements here of protons. But the point is, the lower energy, the 15 and 100 MeV protons, for example, will only hit the atmosphere of Mars, whereas the higher energy, let's say 220 MeV protons, can actually hit the surface. So that's what this cartoon is showing here. And what I'm pointing to at the bottom panel are the measurements from MSL, the radiation detector. So the MSL rad, they make measurements at the surface, and they're constantly measuring the radiation from galactic cosmic rays. That's always there in the background. But if there's a solar energetic particle event that occurs, they can actually measure an increase in their dose rate. So that's what you see here. So if you're following along, if you follow the, you see the blue vertical dash line here, labeled E at the top, that's for energetic particle. At least I marked the onset, the beginning of the event measured at Mars. And if you trace it down, you can see, MSL rad measuring the dose rate, and you see an enhancement starting just before September 11th. And they see an enhancement because apparently greater than 100 MeV, 50 MeV particles, protons, reach the surface. And so they saw this enhancement in their background. And that was very exciting for them. This was the fifth event that they measured, and by far the largest enhancement they've seen so far. And they've been around since 2012. Okay, so the enhancement that they saw was a factor of 2 to 3 above the background counts. And I color coded so that you can see the sort of cartoon again on the right hand side here. And now the lines are color coded by the time series in blue and green, showing the same population of particles measured by MAVEN. And so you can see sort of the timing of when MSL saw enhancement on the ground and the timing of when MAVEN in orbit measured an increase in their count rates from these high energy protons. And if you notice the time series here for MSL rad, you can see the enhancement going on, and you see a decrease here. I'll get to that in a little bit. Okay, so I talked earlier about the motivation for why do we study space weather at Mars? And one of them was, we want to send humans to Mars one day to live there, to explore. And so how much radiation exposure will an explorer get in orbit, in transit, and also if they're living at the surface? Okay, so this bar graph shows sort of the dose equivalent measured in units of millisieverts. At the bottom here, you can see different categories of dose measurements. So if you start from the left, the annual cosmic ray dose you get is less than, it's around 0.3 millisieverts. And if you make your way all the way to the right, the red bar, that's, how much dose will you get if you spent 500 days on Mars? And these are, this value for the dose was measured by MSL rad. And the bar next to it, the orange one, is, how much will you get if you spent 180 days leaving Earth and then traveling to Mars? So the dose is actually pretty high compared to what you would get just living here on planet Earth, the far left one, just from cosmic rays that sort of make it, the radiation that you get from cosmic rays. And, versus if you had a abdominal CT scan, which is this blue bar right here. Okay, and if you look on the far right, I kind of label in arrows, what's the dose that you would get from a very strong SEP event. And when I say strong, I mean if you're an observer magnetically connected back to the source of the eruption of the sun. So if you're directly connected to the source, right when the eruption occurs, a CME or even a flare, you can get a really high dose of radiation potentially, because the energies of the particles are really strong at that point. Okay, so I put doses from a single GLE. So GLE is a ground level enhancement event. That's what it stands for, GLE. So if you're magnetically connected to the source back of the sun, right when the eruption happens, you can get a really strong dose of radiation. And one strong GLE can produce a dose equivalent of several quiet years all at once. At Earth, we measure GLE events, and typically the GLE events are measured when we have 1 giga electron volts, 1 GeV protons hitting the atmosphere. Now, if one GeV protons hit Mars, I think that's really strong radiation dose, but that hasn't happened yet. We haven't. Well, probably happened, but we haven't measured anything yet. So stay tuned for that. Okay, well, where does the September event fall on this scale? And I will get to that in a few slides from now. Actually, I'd like to pause here. Are there any questions?
No one's posted any yet, so just a reminder to everyone, if you have a question for Dr. Lee, and if you're on the Zoom, please do type it in the chat box at any time, and we will take a couple minutes to answer questions at that point. And if you're just on the phone and you aren't on the chat box, please pass your questions along to Kay Ferrari and the others with the NASA group, and we will make sure to get the questions answered at some point.
Okay, thank you. Okay, so I want to sort of transition a little bit. And I want to go back to the time series plots I showed earlier. There's more panels to talk about. What I'm showing here is the orbit configuration of 2 spacecraft. One is MEX and one is MAVEN. So if you just focus on panel A here, during this event, both MAVEN and MEX, they're in highly elliptical orbits around Mars. And so there's a segment that is furthest away from the planet, and there's a segment that's closest to the planet. During this event, so if we want to measure the space weather conditions around Mars, it's ideal if the furthest segments of either for either missions, they're what we call well upstream, meaning that it's not tucked inside the plasma environment around the surrounding Mars. So in this case, what we talk about is the bow shock of Mars, or the magnetosheath, or what we call the tail. So that's on the night side of Mars. We want to be well upstream. So if you look at my mouse, that's in the direction of the sun. So you can see Mars kind of shaded red and black. So the red is to indicate the day side, the black is to indicate the night side. We want to be on the day side of Mars. We want to have the furthest orbital segments of the mission, of the spacecraft, on the day side, but very far away, so that it's cleanly measuring, different parameters, the different conditions of that we'll call space weather. So charged particles, the solar wind, we've got densities, particle densities, temperatures, magnetic field. Okay, so the point is, during this event, the furthest segments for MAVEN was not well upstream on the day side. It was actually kind of hovering what we call the dawn-dusk terminator. So you can think of, if you're the sun and I'm Mars, and I hope you can see my hands here, I would like the furthest segment to be between me and you right here, but it wasn't. It was actually over here on my left side. But Max, actually, its furthest orbital segment was well upstream. So ideally, it could have made like really nice, continuous measurements during the event. But unfortunately, at some point during the event period, it had to go into power conservation mode. So the measurements that were upstream weren't continuous, and there wasn't a lot of it. So me and my teammates, we spent a lot of time sort of stitching together all the different pieces of measurements that we can get from any instrument to sort of get the bigger picture of what was going on when the CME impacted Mars. Okay, so jump back to this. Focusing on these other panels here. So talk about energetic particles in panels B and C. And what I'm pointing here is this sort of small feature. You see like this dip, that what I think is a feature that occurs in particle measurements. If you see, you're measuring charged particle measurements, and sometimes you see if there's a CME event and the CME passes by the observer, in this case, the instrument, for example, if the magnetic structure of the CME passes over the observer, you can see a dip in these particles and the particle fluxes. So that's what I'm pointing here. Is this dip caused by a passage of the CME, the magnetic structure of the CME? I'm not sure yet, because we need pretty detailed magnetic field measurements to determine that. If you look at panel I, where my mouse is located, you can see these red dots. These are MAVEN measurements, and the measurements were really sparse. And we stopped making measurements for a few days, in fact. And unfortunately, when we stopped making good, well upstream measurement, that's when the CME sort of passed by us. And how do I know the CME passed by us? Okay, well, if I believe the WCA-NLEL simulations that I showed you earlier, if I believe their predictions for when the CME were to pass us, would impact Mars, it would have occurred on September 13th. So you can see in panels F, G, H, and I, these black solid lines that indicates the modeled time series for the parameters I'm showing here. And based on the predictions, we think that the CME was going to pass Mars around 2 o'clock, 3 o'clock UT, Universal Time, on September 13th. But if I look at the particle measurements, for example, if I look at the electron time series measurements, so time on the x-axis, and you can think of count rates on the y-axis, you can see this. You can see a steady increase in the particle count rate, and then you see this really like sharp spike here. That's an indication that the shock front. So you got the CME itself, and you got the shock front ahead of it. That's an indication that the shock impacted Mars. So that's one clue there. And then we also look at, okay, so then going back to panels F through I, I'm showing the red dots here, that's from MAVEN. The blue dots are from MEX. So this is what I mean when I said that at some point, it went into a power conservation mode. So it was steadily measuring upstream space weather conditions through the 11th, and then it went into this mode. And so you see this big observation gap by MEX, and you definitely see observation gaps by MAVEN. Okay, so I'm looking now at panel J, which is right below I. You can't see the label. And this is a little bit complicated figure, but the point is to show you got blue, you got the green, and you got the red. It's basically showing so you got the interplanetary magnetic field, it's emanating throughout the solar system. And when it encounters an obstacle, like a planet, like Mars, the field lines, they kind of drape over the planet. And so this is what this, and the level of draping, if you have just your nominal solar wind conditions, there's no CME event going on, that draping kind of stops at some altitude above the surface of Mars. But if you have a CME event, that draping can actually be lower. And that's what this panel is basically showing, that the draping of the magnetic fields was actually lower when a CME event was happening. And so, and the deepest draping that my colleagues saw using measurements from MAVEN, they saw the draping going as far down as 300 kilometers above the surface of the planet. So that's what we call a deeply draped configuration. And that was indicative that, the CME was impacting Mars and was passing by. So one more sort of piece of the puzzle for, giving us an indication for when the CME, impacted Mars was from the MSO-RAD dose rate measurement. So I mentioned this sort of dip that you saw in the enhancements right here. So first you see the background count, the background dose, and then you see the enhancement from high energy protons reaching the surface. So you see an increase in their dose, and it slowly tapers off, and then there's this big dip that occurs after that. So after the 13th. So that's indicative of a CME. And so a CME, has a complicated magnetic structure. And that's what I'm showing here on this slide. It has a complicated magnetic structure. I talked about the shock front. So, if you've ever been on a boat and you're like, sailing on a boat, and if you go to the front of the boat, I don't know my boat lingo, so excuse me on that. So if you go to the front of the boat and you look down at the water, you see sort of this sort of draping of you see this like sort of bow shock, a shape of the water sort of draping over the nose of the boat. That's what we call the bow shock. So the CME kind of forms a similar bow shock with magnetic field lines. And so you got the shock front, and then you got these sort of compressed magnetic fields creating the sheath, and then you got this sort of complicated magnetic structure of the CME. So it looks sort of like a loop here. We'll call it a magnetic flux rope. We call it magnetic flux or magnetic cloud. So depending on the direction of the CME, like if it's coming right at you, or if he's just skimming you as an observer, you can see, if you're an observer and you're measuring dose rate, from galactic cosmic rays and from other charged particles. So you see the steady background, and if you suddenly see a dip, because of CME passing by, you can get, different shapes of that dip depending if the CME is coming towards you, like head on, or coming to you at the side. So that's what these two sort of time series are showing. Depending on how you skim the CME, you can get a very sort of a deep feature, like shown in A, or just sort of get a gradual feature shown in B. Anyway, so a CME is a magnetic barrier for galactic cosmic rays. And so that's why you see a decrease in the dose rate. Is because the CME was passing by Mars and is sort of blocking the galactic cosmic rays from reaching the rad detector at the surface. And so this is the biggest decrease that they've seen so far. And they've seen a lot of what they call these Forbush decreases at Mars from other interplanetary structures besides CMEs, but this is the biggest one that we've seen from a CME thus far. Okay, so going back to, so keeping that in mind, so if you look at this time series here, if you start from the beginning on the left side, so September 10th and well before September 10th, I'm not sure, you see this sort of steady background of dose being measured by MSO-Rad. And they see this enhancement from energetic particles of protons reaching the surface. And then you see this gradual decline and then a very quick, very deep dip from the magnetic barrier passing by Mars. So in terms of radiation hazards, people often talk about they don't talk about what's the 1 day dose. They talk about like a more longer term dose. So I've seen numbers like 30 days. What's the average dose that you get over a 30-day interval? Well, okay. In this case, for this event, where does the September 2017 event fall on the scale? It wasn't very high, and it wasn't where this blue arrow is located. And that's because Mars was not magnetically connected to the source of the activity at the sun when it occurred, because then you would have gotten the really high energy, what we call the 1 GeV protons, the radiation from that. Because Mars was not magnetically connected to the flare-to-semi activity region, even though MSO-Rad measured a really large increase in the dose, it wasn't probably the strongest that it could have measured if we were well connected to the activity region. And so the September event actually fell on this scale here in terms of millisieverts. So I mark it right here in this plot here. So it's actually quite low. And my colleagues who were studying this, the MSO-Rad folks, I mean, for them, they said this was a sort of what they call a medium class event. And it was very exciting, but they think that if we were magnetically connected to the source at the sun when this event happened, it would have been, the dose would have been much higher. So I guess this is good news for people who want to go to Mars and live there. If we have solar events going on, it won't be life-threatening if this event were to happen again. And you have to keep in mind that it was a combination of the enhancement from the SEPs and then suddenly the decrease in the CME. Those two effects combined together sort of gave you the average dose that wasn't very high. Okay, are there any questions before I jump into this?
Folks, any questions? We've got about 10 minutes left. So if you have any questions, please start asking them now.
Okay, I'm gonna keep going. Okay, so I want to now talk about auroras. So jumping back to these time series plot, now I'm focusing on panels D and E. Now I'm showing energetic particle measurements by a lower energy. So panel D is measuring lower energy protons, and panel E is measuring energetic electrons. And part of the reason why I'm showing this is because, you need charged particles to make auroras. And so what I'm showing here on the left are the measurements from a measurement called IUVS on board MAVEN that's measuring the CO2 plus what they call the UV doublet. It's an indicator for aurora. And so what I'm showing on the x-axis is the intensity measured in units called kilorayleigh, and altitude. And so they're measuring CO2 plus the UV doublet during this event, and they see this profile here, which, if you go from the high altitude to low, it starts to increase in intensity, and it reaches a maximum around 60 kilometers. And this is for September 13th of 2017. So during the charged particle, when we see a high flux of particles, but also when the CME event was happening. And this is what they call very bright, very, very intense, so very bright signature. And if you look when they look at other measurements from IUVS, they were able to sort of put together a collage shown here. So here's a movie that's showing the aurora, what they call a diffuse aurora, a global event that is occurring at Mars. So the diffuse, so going back to charged particles, so charged particles, gyromagnetic field lines, and for the particles to make auroras, it has to, these charged particles like the electrons and protons, they they hit the atmosphere of Mars and interact with the different molecules and the ions to excite them. And when that excitation occurs, you emit photons and you can see the aurora. And so that's what's happening here. And this is very exciting because this is the second time that MAVEN IUVS saw what we call this global aurora, but this is the first time that they got so much imaging for the event. And so one person has asked before, well, what color would this aurora be if a human was standing at the surface of Mars looking up at the sky and seeing these aurora events? And my colleague Sonal Jain was saying that it will probably be green. So the wavelength would be 558 nanometers. And so here's sort of like a before and after of the aurora. So before the angelic particle events were happening, before the CME event was happening, before it encountered Mars, IUVS was, taking their images in little swaths. That's why you see these little rectangles. And, it was, nothing really much happening on the left-hand side, so September 9th. And then if you look at the event on the 13th, during the peak of the event, you can see what we call the edge or the limb of Mars, really bright, but you can also see brightening across the entire disk of the planet. So that was really neat for IUVS to see this. And what's really neat too, if I will go back to the comparison of Earth also saw an aurora event due to the solar activity last year. So you got two simultaneous, my colleague Don Hassel was like, you see two simultaneous aurora events going on in the inner solar system because of the solar activity last year. So I think that's pretty cool too.
We have a question.
Yes.
Could you, it's not about the auroras, that's really, it's one of the things you've talked about now a little bit. Can you explain a little more about what it means to be connected magnetically to the source, that connection between the sun and Mars and the sun and Earth, yes. And how does being connected versus not connected affect that level of radiation?
Okay, so let me go back way to the beginning because I think this will best illustrate. Okay. So let's look at panel A. So panel A, you have Earth. So that if you can see my mouse hovering around this green dot, that's Earth. You can see this dashed black and white line here. That's the magnetic field line. So the Earth's magnetically connected back to the sun. So if you follow this line back to the sun, so if you follow this line back to the sun, that's where the active region at the sun was located, and that's where the flare activity happened. That's where the CME erupted. And so right when the CME erupts, or right when the flare erupts, there's a whole burst of particles coming out. And these are the highest energy particles because the acceleration of particles is the strongest right at the sun. Okay, so the strongest acceleration is happening at the sun, and because Earth was magnetically connected to the strongest connected to accelerate when it was strongest back at the sun, it probably saw, it did see GeV particles, very high energy particles. Now, if you look at the same panel, if you look at Mars, and you follow this curved field line back to the sun, it's connected to this side of the sun, which is far away from the active region, far away from where the flare went off, far away from where the CME just erupted. And so none of the assets at Mars measure any GeV protons, and it didn't measure any high energy protons, whether at the surface or in orbit, until I want to say half a day, about half a day later. Okay, so you got to think about the timing too. Mars wasn't, according to the simulation shown here, so the snapshot of it, Mars was not magnetically connected. So, okay, if you go to panel C, if you look at the same, black and white dash field line, that field line is sort of brushing sort of the contour of the CME here. So there's just a cartoon, the black contour of the CME. If you go to panel D, I would say that Mars is starting to be magnetically connected to the CME, but to the flanks, we call it, the flanks of the CME. And if you go to panel F, now, not only is, I want to go panel E. If you go to panel E, Mars is still magnetically connected to the CME, but more toward what I call the nose, the center of the CME. And here, so if you think of the acceleration of if you think of the shock, and it's an accelerator for particles, the strongest part of the accelerator is at the nose of the shock. And as you move away from the nose, the acceleration of the particle is weaker. So you can think of it that way. So hopefully that answers your question about magnetic connection. Is there anything else I can think of?
You said yes, thank you so much, it did.
Okay.
We've only got just a few minutes left in the presentation, so thank you.
You're welcome. So, okay, I'm almost finished. Okay, so why do we study, I want to go back to this question, like why do we study solar storms at Mars? Well, because we want to understand the space weather effects on atmospheric loss over time to answer the question, like where did water go in the past? And okay, so prior to this event, there were calculations made in terms of atmospheric ion loss rate at Mars. And this based on the observations prior to the September event. And the number that was calculated based on the total ion loss rate was about 100 grams per second. And you know, my colleague Dr. Dave Brain at last was being interviewed about this along with the PI, the MAVEN mission, Richard Tchaikovsky. And he was asked this question, he said 100 grams per second, but he also said that he couldn't help but to think of, you know, hamburgers flying off of the Mars atmosphere. So I like to have this picture in my mind, and I tell people, you know, in terms of how much mass is being lost per second, you can think of a cheeseburger flying off Mars every second. That's the current loss rate. And, you know, what's the loss rate that was determined for the September events? Because this event was actually quite strong. Okay. And I asked her, you know, do we get Big Macs instead of quarter pounders? Well, we don't know exactly. This figure is from the PI, Bruce Tchaikovsky. I kind of stole this from him. But it's a plot that I've shown in the paper. And so it's a histogram, and the x-axis is basically showing what we call solar zenith angle, where 0 is at, you know, 0 is pretty much Mars and the sun, and here's 0. And then, you know, 90 or 270 is pretty much at the edge of the terminators between the night side and the day side. And so the black histogram show here is just the average from the entire mission so far. And the red dots you see here are measurements made during, measurements that are, the loss rate that's inferred from measurements that were made during the September event. And the X's right here show the average outward flux. And so the point is, I want to make is that this September event, it was above average, but it was a single point measurements that are being made here. That's what I talked about earlier. There's a single point measurements being made in terms of loss, and there could be greater loss elsewhere on the planet that wasn't being measured. And so you have to think of the average loss in the end, and this is just single point measurements. So based on the single point measurements that are made so far, the loss was above average, but we have to be a little bit careful about interpreting this. And so what I wanted to end with was, again, showing the two motivations for why we're studying space weather. But, you know, we're hoping to get more solar storms happening at the sun, and hopefully, you know, if things are lined up properly with Mars, we can actually make more measurements of the effects at Mars due to space weather. We want to have more measurements in order to figure out, you know, what's the loss rate of the atmosphere due to strong space weather events, like when a strong CME occurs. But we also want to know, well, what's the charged particle radiation environment like when there's a really strong SEP event going on, meaning when if we're magnetically connected to the source back of the sun and we actually get the GeV protons hitting the surface, you know, what's the damage to be done if a human was to be at the surface? So I want to keep, you know, this is the driving motivations for why we want to study space weather and why I'm interested in space weather as a whole. And with that, I think that's the end of my presentation. Thanks.
Awesome. We have one final question, and that was, as we become better at predicting CMEs, could telescopes in orbit around Earth, like Hubble, observe aurora on Mars?
Oh, I would Well, hold on. That's a tricky question. And I'm not an aurora expert because I know Hubble have seen auroras at Saturn, I think at Jupiter. I would like to say yes, but I know IUVS on MAVEN has to be in a special configuration to see the brightening. I don't know is my best answer. I would think so, but I don't know.
From what I understand, some of the auroras are located, they're located in a different way than the auroras on Earth and Jupiter and Saturn, yes. So it's probably, with a different mechanism, it might be a little harder. I don't know.
Yeah, I don't know. I should ask this to my colleagues next week when we have a meeting.
Well, everyone, please join me in thanking Dr. Christina Lee. Dr. Lee, people are posting comments about how they're very thankful. It's fascinating. Thank you for your time, and they enjoyed the